and B are diagonalizable matrices, it need not be true that A plus B or A minus B is also diagonalizable. If matrix A is 1, 1, 0, 0 and matrix B is 0, 0, minus 1, minus 1, we can see that A and B are diagonalizable matrices because A is an upper triangular matrix with distinct diagonal entries 1, 0 and B is a lower triangular matrix with distinct diagonal entries 0, minus 1. Hence A and B are diagonalizable. Let us check whether A plus B is diagonalizable or not. Corresponding to distinct eigenvalues, there always exist distinct linearly independent eigenvectors. And that is why we can conclude that a matrix with distinct eigenvalues will always be diagonalizable. Let us verify it for matrix A and matrix B. Consider matrix A 1, 1, 0, 0. We have the eigenvalues are lambda equals 0 and lambda equals 1, which can also be verified using the characteristic equation. To evaluate the eigenvector corresponding to lambda equals 0 and x1, the column matrix which is the eigenvector, we have the matrix multiplication A minus lambda I into x1 equals 0. After multiplication, we obtain the equation x1 plus x2 equals 0, from where we have the general form of eigenvector for lambda equals 0 is given by minus k, where k not equals 0. If we adopt the usual shortcut method here for evaluating x1 and x2, we obtain both x1 and x2 as 0, which gives us a 0 column matrix x1 to be the eigenvector, which is a contradiction. The shortcut method is a failure here because this matrix has only one linearly independent row, which is the first row. 0, 0 row cannot be considered as a linearly independent row. It is only a dependent row. So we have to strictly multiply the matrix and find out the expressions for x1 and x2. We obtained x1 equals minus k, where k not equals 0 is the general format of eigenvector for lambda equals 0. Similarly, for lambda equals 1, we obtain the eigenvector x2 equals k0, where k not equal to 0. Since we obtained two linearly independent eigenvectors here and the order of the matrix is 2, we have A is a diagonalizable matrix. Same is the case for matrix B. We have eigenvalues lambda equals minus 1, lambda equals 0, and corresponding to distinct eigenvalues, we are able to obtain linearly independent eigenvectors. And since we obtained two linearly independent eigenvectors and the order of the matrix B is 2, we can conclude that matrix B is diagonalizable. One more observation with regard to matrix A is that here sum of all columns remains 1. So 1 is necessary an eigenvalue. Another observation attributed to B is that sum of all columns remains the same, which is equal to minus 1. So minus 1 is necessarily an eigenvalue of B. When you consider A plus B also, you have the same observation. Sum of each column remains the same. Sum of each column equals 0. So 0 must necessarily be the eigenvalue of A plus B. We can also verify it using the sum of eigenvalue equal to trace of the matrix 1 minus 1 equals 0, and the product of eigenvalue equals to determinant of the matrix, which is equal to 0. So lambda 1 and lambda 2 should be 0 itself. You can also verify it using the characteristic equation determinant of A plus B minus lambda I equals to 0, and from the equation you have 1 minus lambda square equals 1, from where you obtain lambda equals 0, 0 are the repeated eigenvalues or repeated roots of the characteristic equation. We wish to find out the eigenvector corresponding to lambda equals to 0. We consider the matrix multiplication A minus lambda I into x1 equals 0 for lambda equals 0 and the column matrix x1 equals x1 x2. We have x1 plus x2 equals 0 after the matrix multiplication. So x1 equals minus x2 is the relation to be satisfied by the entries x1 and x2. So we have the general format of the eigenvector corresponding to lambda equals 0 given by x1 equals k minus k, where k not equals to 0. Since we obtain only one linearly independent eigenvector corresponding to lambda equals 0, we have to conclude that A plus B is not diagonalizable because A plus B is of order 2 and the linearly independent eigenvector obtained is only 1.